And thus it begins. So, warm up today. Suppose we have the vectors u, v, and w. Find the length of v. I think you can all find a length now, right? It's like a three-way distance formula. So this square root of 3 squared plus 2 squared plus negative 1 squared. So you end up with root 14. And looking at your boards, it looks like you all got root 14. So that is fine. Good. Find a unit vector in the direction of v. To find a unit vector, you just take the vector and divide it by its magnitude, right? So it's just v divided by root 14. That's going to come in big today. We're going to kind of use that in an interesting way. Are any of the vectors parallel? This was where some of you got a little stuck because how do you know if the vectors are parallel? It's not like I've taught you anything like the slope of a vector, right? How do you know if they're parallel? So, Pranav, how are you today?
Good.
Good. Thank you. Yeah. No, I'm doing fine. Weekend was good. Yeah. Did you do anything fun this weekend?
Went to work.
Went to work. Where do you work?
Best Buy.
Best Buy. Wait, so is Nathaniel? And then I had a student, at least one or two last year, who also worked at Best Buy, but I don't know if they still work there. What? Oh, Troy works at Best Buy?
Yeah.
Does he still work there?
I think so.
Okay. All right. So, all right. Well, good. Do you guys what section of Best Buy do you work in? Customer service. Is it a Best Buy? Is there one in Eden Prairie?
Yeah.
Okay. All right. I have not been in that one. So quick story. I'll let the thing run. We had to go we were in Shakopee at the Tires Plus, and we were getting something done with the tires on my car, my husband and I. And so it was going to take like an hour, not something super long, but there's a Best Buy right by there. And so we're like, well, we'll just wander over and wander, because Best Buy's kind of fun to wander around in, right? It's a nice wander store. Do you guys get a lot of people who just go in there and kind of wander around? Yeah. So we're wandering around Best Buy, and we ended up buying a refrigerator. Like, we weren't even planning on it. It just happened that way. And so we walked out, and we were like, all right, now we have a refrigerator. So anyway, yeah, it was a great deal, though. It's like the best deal I've ever had on a refrigerator. Really nice. Stainless steel, stuff side, like all like the ice maker and everything. Guess how much I got it for? Out the door, including shipping.
$500.
$600. Not bad, right? For a nice brand new refrigerator, but it's been on the floor for a while. It was a floor model, right?
Oh.
So anyway, we got a great deal on it. So yeah. So once in a while. Anyway, so that being said, Pranav, you had a method for determining that there were some parallel vectors mixed in here. Which ones did you think were parallel?
U and W.
Tell me why.
Because one is the scalar multiple.
Yeah, because if you look at U and W, if you take every number of W and multiply it by -2, you get U, right? Or vice versa times -1/2, right? Either way. If one vector is a scalar multiple of another, the scalar in front you can't change the direction by multiplying by a scalar. All you can do is change the length. Well, I lied. You can change, you can point it in the opposite direction, but it's still going to basically be on, if there was an infinite line, they'll both be on the same line. Does that make sense? So even if one's pointing that way and one's pointing that way, they're still collinear, right? So, and we would consider those parallel, if they're going in the same direction, even if they're equal but opposite, we would still consider them parallel. Now, the question that takes us up a notch is does the definition of parallel mean same slope?
No.
Technically, the definition of parallel is not same slope. The definition of parallel is non-intersecting, right? So, yes, these two vectors are parallel, but now you're in 3 space. Are these two parallel? Dun, dun, dun.
What?
The answer is no, they're not.
Okay. That was mean.
But in 2 space, that's that whole talk. Didn't I have a big talk about non-Euclidean geometry with you guys last year?
No.
No, and the whole point about parallel, like hundreds of years spent talking about, if you have a line and a dot, is there, Euclid 2,300 years ago said that there is exactly one line through this dot that is parallel to this line, right?
Okay.
And then that was called a postulate. It was his fifth postulate. A postulate is something that we take as truth without that can't be proven. We just accept it, right? Then in like I want to say the 16 or 1700s, it was probably in the 1700s, mathematicians started saying, hey, that's not a postulate, that's a theorem. We can prove that to be true. If it's something we can prove, then based on prior knowledge, and there's only 4 other postulates, so you had to prove this based only on his 4 other postulates. If you could prove it, it's not a postulate, it's a theorem. So mathematicians spent several hundred years trying to prove that this was true, and then finally what happened?
It's a postulate.
Lobachevsky comes along and proves that it cannot be proven.
Okay.
So he actually wrote a proof to prove that this cannot be proven. So then what mathematicians figured out was they said, if this was such a conundrum, what if it's not true? What if it can't be proven because it's not true? And then they started taking lines and bending them, right? And then after they started bending straight lines, that was when you entered all these new worlds of geometry that were non-Euclidean, right? And thus non-Euclidean geometry was born, right? So if you took a straight line and bent it, that would still be parallel to this line.
Wait,
It would if it's bent, not curved.
But it's not
Right?
the same thing.
Wait, what?
What's that mean?
So like,
Wait, but then how
so
come those
for
like
example,
two aren't
for
parallel?
example, easiest example, your globe, right? You have your longitude lines, those are the ones that go up and down, right? Those lines are straight but bent along the outside of the sphere, right? We consider them parallel even though technically they intersect at the poles, right? And technically they're like not even remotely like they're bent in different directions. Like all these, so you're taking a line and you're bending it along an object, which is why we take the object, like we have elliptical geometry and hyperbolic geometry and spherical geometry. So you're taking straight lines, but you're bending them into a space shaped by some geometrical figure. And then all of those rules just go out the window. Okay? So all that being said, yes, U and W are parallel because one's a scalar multiple of the other. We have such a big lesson, and I get on so many tangents.
But
Okay,
if the
All right.
bent one's parallel, then how come that isn't parallel?
because this is called skew. Let's just stick with Euclidean geometry for now. We're going to stick in Euclidean geometry world. And even in 3D, these would not be parallel. These are called skew. So in 3D, we're going to say that they have what's called the same direction vector, which is basically the same slope. So we're going to go with the same slope thing for this class when we talk about parallel vectors. All right. Find 3 other points that are collinear with those 2 points. So in order to find 3 points that are collinear with those 2 points, did anyone subtract them? Did anyone, tell me an idea. I see a bunch of points on the boards. How did you guys get all those points?
It's more like an intuitive rate of change.
Yeah.
Okay, so you were kind of saying, hey, my x's go up by 1, so then I could just keep going up by 1, right? The y goes down by 2, so I keep going down by 2, and then the z goes up by 3, so I keep going up by 3. Mm-hmm. Okay, which is basically the same thing as saying, hey, guys, do you remember how we talked about how do you build a vector from 2 points? You subtract, right? Subtract, right? Yes? Right? Turn, like, beginning point, ending point, subtract the 2 points, build a vector. So if we had some vector called u, by subtracting those 2 points, you get the vector 1, -2, 3. We would call this essentially the direction vector. And then you just take, which is like kind of like vector world for slope, right? So you can just take, this is kind of saying, hey, to go from this point to this point, I do this operation. Basically, I add this to this point and I land on here. If I keep doing that repeatedly, I'll always land on points that are on the same line because I'm always doing the same change to X, Y, Z to land on the next point. So whatever it is, forward, da-da-da-da, da-da-da-da-da, da-da-da-da-da, right? I'm always going to be on the same line. And we'll do, like, this is just, a lot of this is just to expand. This one, though, you all should have gotten, right? So equation of the sphere. Let's see. So the center, you had to find the midpoint, and then the radius, you had to find the distance and then have it, right? So you ended up with x minus 3 squared plus y minus 1 squared plus z squared equals 12. Well done, guys. Good, good. Oops. Good, good. So you guys did the diameter instead of the radius. Okay, good. So well done. You all got the stuff that you needed to get, right? So that's good. Let's move into today's lesson. Where's my, there it is. Today we're doing dot products. Whoops. Oh, I forgot to change the section number. This should be a 12. 12.3. Dot products. I lied. This is actually a big lie because we're actually doing dot products and projections today. So it's going to be a double extra big lesson. If we don't get to it all, we'll finish it tomorrow, but hopefully we'll get to it all today. So we actually today have to do dot products, which will include angles between vectors, direction cosines. It'll also include projections, work and force, and that'll be it. I think that's the whole lesson. It's quite a big lesson today. All right, so 12.3, dot products. Here we go. There's my girl. Okay. So a dot product is an operation in vector world. So it's really just a defined operation, kind of like multiplication. It's actually a combination of multiplying and adding. And there is a meaning to dot products, which we will start to brush the tip of today. Really, we're going to learn the meaning by just discussing in context some of the applications of dot products. So this is a lot of writing. You don't have to write all of this, honestly. I don't think I've ever once memorized a dot product as this kind of a formula. Let's just talk about what it is. If you have the vector u and vector v, then you take x times x plus y times y. And whatever that equals, that's your dot product. So multiply the x's, multiply the y's, add them together, you have the dot product. If you're in a three-dimensional vector, then you have x times x plus y times y plus z times z, add them together, and that's your dot product. Well, it's like multiplating, right? It's like multiplication and addition. Did you guys do this at all last year, or in pre-cal 2 years ago? Pre-cal a little bit? Okay. All right. So a few properties of dot products. Dot producting is commutative. So u dot v is equal to v dot u. The distributive property holds u dot v plus w is u dot v plus u dot w. If you are doing a scalar times a dot product, it's just like a scalar times a product. Like if people, a lot of times algebra 2 students have trouble with this. If I have 3 times 4 times 5, they think they have to distribute here. But if there's no plus, if it's just times, it's just 3 times 4 times 5, right? So if I have 3 times u dot v, that's either 3u dot v or u dot 3v, either way. Put the 3 in the beginning or the end, wherever you want to multiply that 3. All right, u dot any, or 0 dot any vector is 0. V dot v is the magnitude of v squared. So, and the dot product of any vector with itself is its magnitude squared. And you can play with that for a minute just by picking like letters A, B for V and do a dot product and see what you end up with, and you'll see that you end up with A squared plus B squared without the square root, which is the magnitude squared. All right, but you don't have to memorize those. You just need to kind of know that they apply. Oh, okay, so yeah. All right. How does warm and stuffy? Do I go cold to warm and stuffy? Okay, so quick example. So everyone take a moment. You have U, V, and W. Find U dot V times W, U dot 2V, and the magnitude of W squared, which is kind of doing the last property backwards. So take a moment in your groups and see if you can nail out these four. So U dot V, so you'd have 2 times 5 plus negative 2 times 8. So you get 10 minus 16, which is negative 6. Everyone okay? Questions? All right. So U dot V times W, you're thinking, but wait a minute, what do I do with these? Is it a dot W or is it a times W? Except what is the answer to U dot V? Is it a vector or a scalar? It's a scalar. The answer to a dot product is a number. It's a scalar. So because the answer to the dot product is a scalar, this is just a scalar multiple of W. So U dot V is negative 6, so this is just the same thing as negative 6W. So you just do negative 6 times W.
What does the property mean?
Which property?
Like, there's a property that looks like that, but it's...
Oh yeah, and you could have done, oh, let's see.
But it
That
gives something
was different. That was, you're talking about this one?
Yeah.
This one is a scalar times U dot V. That was a vector times U dot V. Yes.
So in a random way.
All right, U dot 2V, you're just doing the dot product of U and 2V, so you end up with negative 12. Did you notice U dot 2V would be the same thing as 2 times U dot V, right? So you could have just taken your answer, negative 6 times 2. All right, and then the last one, the magnitude of W squared is the same as the dot product of W and W, right? Just W times itself, so you end up with 25. How did we do? Brian, we good? Yeah, okay. All right. Angle between two vectors. First application of dot products. They get used to find the angle between two vectors. So if theta is the angle between two non-zero vectors, U and V, then the cosine of theta, so theta is the angle between two vectors, cosine of theta is U dot V over the product of their magnitudes. We're going to use this all semester. So this is a big deal. Cosine of the angle between two vectors is their dot product over the product of their magnitudes. Because of this, it actually gives you a new definition for dot product. So we could actually rewrite this to say, hey, the dot product of U and V is equal to the product of their magnitudes times the cosine of the angle between them. So it becomes an alternate definition for dot product. So dot product helps give you the angle between two vectors, but it also has an alternate definition based on that. So you have dot product of U and V, V being, x1, x2 plus y1, y2, or magnitude of U, magnitude of V plus sine theta, where theta is the angle between. So based on this, if the dot product is 0, now these are two non-zero vectors, right? So if this is 0, well, this isn't 0 and this isn't 0 because the vectors have a length. So this has to be non-zero. This has to be non-zero, which means the cosine of the angle between them has to be 0. What angle has a cosine of 0? Pi over 2, right, or 90 degrees, which means if the dot product of two vectors is 0, those vectors have to be perpendicular. Or orthogonal, which is the appropriate vector world term. Orthogonal. So when you see orthogonal in vector world, that means perpendicular. So anytime you have two vectors with a dot product of 0, it means that they are orthogonal or perpendicular. All right, take a moment and find the angle between these two vectors using this formula right here. So cosine theta equals u dot v over the product of their magnitudes. There's u, there's v. See if you can find the angle between u and v. You will need a calculator probably. So, wish I could move this. Here we go. So the cosine of the angle, there's the dot product on top, 3 times negative 4 plus negative 1 times 0 plus 2 times 2 over magnitude of u, magnitude of v. So you end up with negative 8 over root 14 root 20, or simplified negative 4 over root 70, which is still not totally simplified, but that's all right. So, so you get that. Is that the angle? No, that's the cosine of the angle, right? How do we find the angle? We've got to do arc cosine or inverse cosine of that to end up with the angle, which is 118.5. Is that okay? Good. By the way, so that is saying that the angle between these two vectors is 118. So I've got these two vectors. By the way, the vectors can be skewed. That's okay because you just remember we don't have a location. Vectors don't have a location. They just have magnitude and direction. So you can line them up, right? So whatever they are, this says the angle is 118-ish degrees like that. Is that the only angle between these two vectors?
No.
No, because if you think of them like that, there's always two angles. There's an obtuse and an acute, right? Unless they're perpendicular. So if you got whatever 180 minus this is, that would also be correct. Ryan, did you get that?
Initially.
Wait, how did you
Okay.
get that?
Yeah. So if you didn't put the negative in,
Oh.
right? Is that what you did? Okay. You know what? You'd still be correct, though. You accidentally found a correct answer. So well done. All right.
This price is this the angle from like the XY plane?
Is this what?
Like the angle from the XY plane?
This would be the angle in no plane. It's just the angle between two vectors. Doesn't matter where the vectors are. They could be like this way. It's the angle between those two. But funny you should ask about the XY plane. Oh, before we get to that, sorry, one more. All right, I like. So orthogonal, parallel, or neither. So find the dot product for each of these. Take a second and then determine if the vectors are orthogonal, parallel, or neither. Think about, just go ahead and do it. I'm not going to tell you. Hi, Ian. How are you? I'm doing great. How was your weekend? Did you work at Best Buy? No? What did you do? Okay. Did some homework, video games. Oh, that's good. That sounds like a very nice, weekend. Nice average. If you had to pick one video game to play, what would it be? Oof. That's tough. Not Fortnite. Okay. What would it be? League of Legends. Anyone else play League of Legends? Oh, two gentlemen in the front.
Oh, no.
Oh, Nathan went no. Okay.
An exterior.
That's okay. So, all right, good. Ian, so for the first one, did you decide if those two vectors were parallel, orthogonal, or neither?
I concluded that
Orthogonal? Tell me what brought you to that conclusion.
the dot product is zero.
The dot product was 0. Did everyone else come to the same conclusion?
Yes.
Yes. All right, good. So, Sophie, how is it going?
Good.
Good. So, I'm calling on Sophie because I was kind of listening in on her conversation when she was working on the second example and didn't even have to do a dot product because she figured out what? What did you figure out?
They're scalar multiples, so they're parallel.
They're scalar multiples of each other, so they're parallel. You did it in the warm-up today, right? So since, like, ignoring the negative 1/3, just look at that guy and that guy. All you have to do is double it, right? So these two are scalar multiples, which means they are parallel. Well done. Okay, direction cosines. So speaking of, hey, we know how to find the angle between two vectors, but how do we know what angle a vector makes, like, in the world? So we get out our beautiful octants, and I say, all right, so you've got some vector in space, right? Say the vector is like here. Okay, so I can take this vector in space, I can move it so that it starts at the origin, right? Any vector can be moved so it starts at the origin, because technically you're not moving it, it just is, right? A vector just exists. So here we go, starting at the origin. So what angle does this vector make? Well, what angle does it even make sense? Like, how do you know what angle to even talk about? There's a whole lot of angles here, right? So what we do is we use what are called these direction cosines. And the direction cosines tell us the angle that the vector makes with each axis. So this vector makes an angle with the x-axis, the y-axis, and the z-axis. And once you know those three angles, then you kind of know, like, the position of the vector in space. So each vector, we don't use these a ton. They come up a little bit. These are not nearly as common as the angles between two vectors, but they'll come up a tiny bit. So direction cosines help us to know the angle of a vector just in space in general. So this whole big convoluted thing is showing you how do you like calculate a direction cosine. So the first one that we're calculating here is the angle between the vector and the x-axis. Well, how do you do it? You're just using your regular old angle between two vectors formula, and for the x-axis, you're using the vector 1, 0, 0, right? So if we use this vector 1, 0, 0, we give it a length of 1, right? So if we find the angle between these two vectors, you end up with actually just the x component of your vector divided by the magnitude of the vector. And that gives you the angle with the x-axis. And then the same thing goes for y and for z. So for, we call it cosine alpha, beta, and is that lambda? Lambda. So alpha, beta, lambda. So anyway, so cosine alpha, so the angle between the vector and the x-axis is the x component divided by the magnitude. The angle between the vector and the y-axis is just the y component divided by the magnitude, and the z-axis is just the z component divided by the magnitude. Now those are the cosines of the angles. To find the actual angles, you still have to take the arc cosine for each one. And if you forget these, you can always go back and do just angles between two vectors and use 1, 0, 0, 0, 1, 0, or 0, 0, 1 for your other vector. And that will give you the angle of the axis. Those are called the direction cosines. Writing, I'll give you a minute. our old book put projections that we're doing in a minute in a totally different spot. And our new book has them in with dot products, and the way that the calendar worked, we had to kind of squish them together. So we're kind of doing 2 days of lessons today in 1 day. I think we got it. We find it. All right, everyone. Nick, how you doing? Are you? Okay.
Sorry, I'm a really slow writer.
You do not have to apologize. I'm a slow reader. You know, we all have our gifts. Right? All right. Okay. One major property of direction cosines is that if you square each of them and add them together, you get 1. So the reason for that is that the vector itself over any vector over its magnitude is 1, right? It's a unit vector. So you end up with, since the vector over its magnitude is equal to the sum of each direction cosine times the I, j, and k vectors, you end up with this whole thing equaling 1. We don't use this property very much. It's just like, oh, it's kind of cute. So I don't remember using this. I don't know if we use it at all. So, but it's like a handy little thing. Okay, so we're going to take a second, find the direction cosines, and then the actual angles with each of these, the axes for the simple vector v, which is just 2, 3, 4. And then just square each of your cosines and add them together and see if you get 1. So take a minute. Let's just practice finding direction cosines, and then we'll get into projections. Okay, so your magnitude is root 29. Your cosine alpha is 2 over root 29, so the first angle is around 68 degrees with the x-axis. Cosine beta, 3 over root 29, so beta is around 56 degrees with the y-axis. And then this is a gamma, so sorry, cosine gamma, 4 over root 29, so gamma, which is the angle with the z-axis, is around 42 degrees. And then a quick show that, yes, when you square each of the direction cosines and add them together, you get it. Okay, just so you know, these numbers, those are called the direction cosines, and then these are the actual direction angles. These should have little degrees on them. These all have degrees. Simple formulas, right? I mean, plug and chug. Okay. All right. Now we're going to get into the good stuff. Okay, so here we go. Projections. So far, we have learned how to take several vectors and combine them to find a resultant vector. Now we're going to learn how to take a vector and break it apart into its orthogonal components. Now, we spend, in these slides, you're going to see me break a vector apart into its projection and then its orthogonal projection. But really, we don't do both of them. Most problems, we just find the projection. And we don't have to worry about the other component of the projection. So anyway, so the forces, I am terrible with properly drawing forces with the arrows pointing in the right directions. I can always solve the problems, but my physics, especially like a box on an inclined plane, those were like the bane of my existence in high school. So I had a lot of students correct me on whether this arrow should be pointing this way or this way. I had students arguing both ways. It really is completely irrelevant to what we're trying to learn. So let's not get too bogged down in which way the arrows are pointing as far as these forces go. Is that okay? Okay. All right. So the forces W sub 1 and W sub 2 help you analyze the effect of gravity on the car. W sub 1 indicates the force pulling the car backwards. W sub 2 indicates the force that the tires must withstand. So one is kind of more gravity-ish, and one, they're both gravity-ish, but one is like pulling the car this way, and one is pushing the car down this way. Does that sound correct? Okay. All right. Even if it doesn't, it's okay, because it's just, for these purposes, we're fine. All right. So anyway, so suppose we know like this force, and we want to find this guy, right? how do we do it if we don't know the angle? And that's where projections come in. So let's talk about it. All right, so here's like the definition, and we're going to use this a lot in context throughout the next couple of weeks, and really actually later on in the term as well. We'll come back to projections. It took me a while, like I can show you this mathematically, but later on I'm going to talk to you about how I describe projections to myself in my own brain that makes them make so much more sense to me than any of this stuff did. So I'll teach you this, and then I'm going to invite you into my brain for a minute. So here we go. So U is equal to W plus W1 plus W2. Just think about this, like if we line these two vectors up tip to tail, right, W1 plus W2, we would get U. U would be the resultant force of those two vectors, right? So you can find two orthogonal vectors that add together to create a vector, right? So W sub 1, you have this other vector V lying here. W sub 1 is a vector in this direction, but it's this component of U. So in this, and we say, and it doesn't have to be the horizontal component. It looks horizontal in this picture, but you could tilt this whole thing and it'd still be true. So we like to say horizontal and vertical, but honestly, projections can be anywhere. They don't have to be horizontal and vertical. They could be oriented in any direction at all. So here's what we get. So W sub 1 is called the projection of U onto V. The projection of U onto V. And what it really is it's the component of U in the direction of V. The component of U in the direction of V. So W1 is also called the vector component of U along V. W sub 2 is just the vector that's orthogonal to W sub 1 that makes up the other component of U. So W sub 2 is really not near as important as W sub 1. We can still find W sub 2, and actually, if you know W sub 1 and you know U, to find this guy, you could just do this minus this and get that, because they add together to get this guy. So this guy really isn't that big of a deal. This guy is the big deal. So W sub 1 is, oh my gosh. It's such a toss-up between noise and temperature. Okay. So there is a formula for calculating the projection of U onto V. When you see this word right here, right, this guy right here, I like to think of V as like, see how V is like the little subscript one? So, and U is like above it. The projection of U onto V. U onto V. So this is, U is like your main vector. V is like some other direction vector. And you want to know the projection of U onto V. So the component of U that would be traveling along in the direction of V. So it's a formula. It's the dot product, it's U dot V over the magnitude of V squared times V. This whole thing right here, that whole big thing is a scalar. It's a number. U dot V is a number. Magnitude is a number. You squared, it's a number. This whole thing is a number. So what is this number? It's like a scalar multiple of V, because V is a vector. It's in the right direction. All we need to do is change its length somehow to create that projection of U down onto this vector. So really what this formula gives you is a scalar multiple of your vector V. To say, hey, we want what U's component is onto V. You use this formula and you're just multiplying the length of V to create that W sub 1. All right, great way to think of it. Oh, yes.
When you say it's the vector component of U, what do you mean by it?
Okay, so U can be, any vector can be broken into a sum of two other vectors, right? So in some direction, you get two vectors that are orthogonal. When you add them together, you get your vector. It's the resultant of the sum of two It's really the sum of infinitely many pairs of vectors, but we're just talking about two orthogonal vectors. You can add them together and create your vector. It's easier to understand in context. Here's how, I'm going to invite you in my brain for a second, okay? So, and it'll help when we have problems to solve. You'll see what this means. But here's what I think, because we're going to do this in multiple dimensions later on. So when I think projection, what I picture is like if you had a light bulb. Come on. Oh my gosh, draw. Okay. And it was shining above, pretend like it's higher, right? Shining straight down on this vector. The shadow that this vector would make along this surface is its projection. That's why I kind of think it's called projection. It's like you're projecting that vector down onto that spot. Because, and you'll see in context in just a minute when we do some problems when this comes in handy. So, oh, yes?
So, U is like the W1 plus W2, but where does V come from?
So, that's where context will help.
Okay.
Okay, V is just it's the direction of one of the components of U. So, we'll show you. And you know, I really should just start with an example. It's hard to know, do you start with the formula or do you start with the example? I am going to walk you through, though, my mindset of when I first was learning projections. So I say they're really horizontal and vertical components of the vector. They're kind of not, but they kind of are. Because, again, you can take anything that's been tilted and kind of tilt it back and get a horizontal and a vertical component. So you can turn them into horizontal and vertical. So anyway. So really very similar to horizontal and vertical components of a vector. Normally we're writing a vector, when we write a vector in trig form, we know that angle. So if you have some vector and you need to write it in component form, and then you know the length and you know the angle, then you have, r cosine theta, r sine theta, and you have your vector in component form. Here, we don't need to know the angle. We have a way to break a vector down into components without knowing the angle. So all you need is your vector and then any vector that's in the direction of the component that you want. So if you have your vector and then say you want the projection of it like its horizontal component, you can use your vector, like say you're in 2D, just the vector 1, 0, do the projection down onto it, and you've got your horizontal component without having to know the angle of the vector. So it's kind of like a way of getting that component without knowing the angle. So that's one use for it. And I do kind of do a little bit of deriving. So remember the length of the horizontal component is r cosine theta. We know this formula for the angle, right? Cosine theta is u dot v over magnitude of u, magnitude of v. And the magnitude of u is the same thing as r. So if I take this is like my cosine theta, right? There's my r, so r cosine theta. This would be my horizontal component of the vector if v was horizontal. Then what happens is those two things cancel. You get u dot v over magnitude of v. Now, u dot v over magnitude of v, think about this. This is u dot v. If I just kind of pull one of these magnitudes under the v, right? So that's this, and then this is a unit vector in the direction of v. So what is this? This is a scalar multiple of a unit vector in the direction of v, and then you get this projection that's the proper horizontal component. So I don't know if that helps, but you know what? Let's just do some problems and then we'll see. All right. Okay. Ooh, I don't want this. Well, you know what? Let's do this first. We're going to crunch out math first. We'll just crunch numbers, and then we'll get into a cute picture problem, and then I think hopefully it will make more sense. And if it doesn't, the world's going to keep spinning because we're going to do these. We've got several weeks, and we're going to do these for a while. So projections aren't going away. Find the projection of u onto v and the vector component of u orthogonal to v, the vector component of u orthogonal to v, that's not near as important as the projection. So this guy, that's like really important. This guy, not quite so much. All right. For the vectors, if that's u and that's v. So like when I was saying horizontal and vertical on the previous slide, that was just to kind of connect it to what you already knew, but v does not have to be horizontal or vertical. V can be any vector in any direction, and what you're doing is you're finding a component of your vector onto another vector into a different. Here, let's see if I can show you the visual. Okay. So say this is u, and say this is v. All right, so u, v. If I want what the component of u is in this direction, right? U is made up of some vector this way plus some vector this way. So how do I get it? So the projection gives me this vector that's along here. And then the vector orthogonal to that would be this guy right here. Here, I'm going to draw it here. I think I might have it under here. I think that's just solution though. But let's just pretend, ignoring this. So we got some vector u, and we have some vector v. So this is u, and this is v. If you extend v out, this vector right here, from here to here, that's the projection of u onto v. That's a v. All right? So it's the component of u along v. The nice thing about it is most of the time you don't need the vector. You need the length of the vector. We use the length a lot because it's the magnitude. The magnitude of that vector is what we're going to use a lot to solve problems. So the projection, you can use part of the projection if you just need the magnitude of this vector. You can use a part of that formula and pull out and just do the magnitude by not including the v over magnitude of v. And then you've got the magnitude of your projection, and you're good to go. Anyway, I don't know if that helps or not. All right, so take a minute, just mathematically, use your formula and see if you can figure out the projection of u onto v. Are you already done? Okay. Just so you know, the second example should take you like 8 seconds.
Wait, Mr. Price?
Yes.
So, like, what's the significance of these projections? Like, what are they used for?
That's what we're going to explore in the next example. I mean, you could write it in right either way. It's fine. I don't care. So this is your projection right here, 14/9, 2/9, -4/9. If you need to find the other component, the orthogonal component, you just take your projection and subtract it from your original vector in order to get that orthogonal component. So it'd be u minus this guy. So u minus that guy.
Is it okay if we just leave it at 1254, 7, 1,
Yeah, that's fine. I don't know if your book accepts that in the. Does your have you guys tried to type in unsimplified answers? Does it take them?
So.
I mean, I've done it with like the multiple up front, but it was a simplified multiple.
Okay. Okay. But it took it?
Yeah.
Oh, that's nice. Okay. All right. Second question. Find the vector component of U that is orthogonal to V, given that W sub 1, the projection of U onto V is 4, 6, and U is W1 plus W2. All you're actually doing is subtracting. This is just checking to see if you know that the two orthogonals add together to give you your original vector. So if you're finding W sub 2, you just take U minus W sub 1, and there you go. And then that's just me showing you, hey, if you do W1 dot W2, you should get 0. All right. Even if you don't understand what it is, can you find the projection by following the formula mathematically? Good. All right. So that's step 1.
What does
Yes.
it says like W2? Sorry, the vector component of U orthogonal to V. What is that?
This one?
Yeah.
Okay.
No, in the first one.
In the first one. So here's what happens. I'm going to draw a picture. It might not be these, but it'll be in general. Okay. So you have U. You have some vector V, right? Okay. So W sub 1 is the vector component of U that is in the direction of V. So
Is that
this red, that's W sub 1. That's called the projection, right? So that's the projection. Projection of U onto V. W sub 2 is the vector component orthogonal to V. And W sub 2 you can find by just doing U minus W sub 1. To get W2?
Yeah.
Because W1 plus W2 equals U?
Oh.
No, it's okay. It's so hard to remember in vector world, right? That you're just doing tip to tail, adding this vector plus this vector equals that vector. All right, I know, this is a lot for your brain to kind of digest, right? It's a lot. All right, now, here's one direct, simple application of projections. It's calculating work done when you're pulling an object at an angle. So the work done by a constant force along a line of motion of an object equals the magnitude of the force times the distance that the object is moved. So the work equals the magnitude of the force times the magnitude of the vector of motion. So if you get a force vector times a motion vector, multiply those together, you get your work. The problem is, if the force is not in the same direction as the line of motion, so like if I'm pulling this box from a rope in this direction, then my force vector and my motion vector are both exactly the same. But if I'm pulling the object, like say the object's moving along the ground, but I'm up here and I've got a rope attached and I'm pulling it this way, right? My force vector now is angled up, even though my direction of motion is still horizontal, right? So how do you figure out the work that's done? You have to figure out the component of the force that goes in the same direction as the motion of the object. In other words, you need to find the projection of your force vector so that it's going in the same direction as your direction of your object. So this can be simplified real easy. Now, you don't have to write all this down. Just stay with me for a minute, okay? You're gonna love it. Once we're done, you're gonna be like, okay, see, thank you, projections, for making my life so great, okay? All right, so here we go. Just wait and see. Okay, open mind. Open right? Okay, so here we go. We need the direction of motion, right? So the vector, this is our motion vector. We need the force that's being applied to the object to be in the same direction as the motion of the object. How do we figure out the amount of force that's in the same direction as the motion of the object? It's the projection of our force vector along the vector of motion, right? So if we call the force vector F and the motion vector V, then it's the projection of F onto V. Gives us the amount of force, the vector of force in the direction of motion. Are you kind of with me? You do not have to write this whole thing, but see if you can follow, all right? Let's just see. Let's play follow along. So here's work. Work is the product of these two magnitudes. It's the magnitude of your force times the magnitude of your direction, your motion vector, right? It's the product of those two magnitudes. This force that's in the direction of motion is the projection of F onto V. So the projection of F onto V, well, that's F dot V over the magnitude of V squared times V, the magnitude of that whole thing, because we want the magnitude of the projection, right? Times the magnitude of V, that's your vector of motion. Let's have fun with canceling, right? So fun with canceling, you've got and let's see, wait. How do I say this? Where did I get my double F from? There's my V squared. There's my V. This V, this V. Oh, it's a magnitude of this guy. Oh my gosh, I'm getting confused. So we get this times this. So I pulled an F out. So here we go. This whole thing right here, that's a scalar. So this whole thing, this is equal to F dot V, that's a dot, F dot V over magnitude of V squared times magnitude of V, right? Because this whole thing is just a scalar multiple times that vector. So it's this times that. So this becomes that guy right there. So now we have a magnitude of V and a magnitude of V over a magnitude of V squared. And after all is said and done, work is actually just the dot product of F and V. All right, so it's because of projections that we can take our work formula and simplify it down to this nice, easy little dot product formula. So what is work? Work is actually just the dot product of F and V. F is your force vector in any direction. V, that's your vector of motion. Have you guys ever done this? Work equals F dot V? No? Okay. In physics? Okay. Did you derive it? Really? Did he use the word projection?
Probably not.
Probably not. Oh, okay.
No, he did talk about that.
Okay.
He's like,
And then you check out. Okay. All right. All right. That's fair. All right. Okay. Let's do an example. To close a sliding barn door, a farmer pulls on a rope with a constant force of, yes, we're using pounds. You need to get over it. Pounds. Okay. With a constant force of 50 pounds at a constant angle of 60 degrees, find the work done in moving the door 12 feet. Oh, I gotta remove this. Well, I'm trying to, oh my gosh, I'm trying to erase. All right, forget it. All right, so work is your force vector times your vector of motion. I'm gonna, let's see. do I have my vector of motion? Just 12 feet? I don't know. See, now I'm thinking 50 pounds. Oh, I just need my vector. And that's why I'm doing my vector. I'm just going to show it to you. Forget it. I'm trying so hard. All right, let's draw a picture. So we have the vector of force. We have the vector of motion. He's pulling at a force of 50. This is an angle of 60. This is a length, a magnitude of 12. And so work is the dot product of F dot V. Now, you don't have F. You could write F in component form in order to do the dot product, but remember dot product, you do x times x plus y times y. We don't have x's and y's. We could write x's and y's, or we could just use this formula, magnitude of F times magnitude of V times the cosine of the angle between them. So I'm doing magnitude of F times magnitude of V times the cosine of the angle between them in order to find F dot V. The other way to do it is you could break F down into trig component form, and it's just the x component of that vector. So it's your magnitude of F cosine theta to get you your F, and then dot V to get it. But anyway, so this, your dot product, so magnitude of F times magnitude of V times cosine of the angle between them. All right, I have another example that I'm not going to reveal the answer to. So 50 times 12 times cosine 60, you end up with 300 foot-pounds, or pounds-feet. Huh?
Where did the cosine come from again?
So we needed the dot product, but all we knew was that we had a vector with a magnitude of 50 and an angle of 60 degrees. And we had another vector with a magnitude of 12. And we didn't have the components for the vector, so we couldn't do a dot product, a traditional dot product with component times components, because we didn't have like the x, y, right? So I used this formula for dot product. Remember the other formula we learned? Which is this right here, and then just taking this and putting it in front. So it's easier. It's the quicker way, rather than trying to rewrite F in component form.
But even if you rewrote F in component form, how do you get V?
Well, you'd have to let V be horizontal and just do, 12, 0.
Okay.
Do a vector of just 12, 0.
Okay.
That's what I would do. And that way, if you let V be 12, 0, and we were to write F in trig component form, so 50 cosine 60, 50 sine 60, right? If we did it in trig component form, what do you get when you do the dot product? You get this times this plus 0, and you end up with the same thing. Blank screen. Nope, I didn't want that. Where's my cute picture with the wagon? Oh my gosh, I lost my picture with the wagon and I went to a blank screen. All right, that's okay. We have 2 minutes left. I'm going to kill this.